Okay, this is lesson 1.2, properties of real numbers. I'm dividing this up into two sections, so we're just going to look at the real numbers right now, and then we'll talk about properties later. Yeah, so let's get started. First, let's focus on natural numbers. And you're probably thinking, hey, I've seen something like this before. When we talk about natural numbers, I always think when you were starting to count, when you were like a little toddler, and you were 3 or 4 years old, if you ask a little 3-year-old to count, they start with 1, 2, 3, 4, 5, and so on, and however high they can go. If they're a genius, they can go up to, you know, thousands and millions, but generally we just start counting like that. So it's called what I call counting naturally. Okay, and what in your notes, not only do I want you to write this little piece down, you know, put an example, what it means, but in your notes then also make a little diagram like this. And these circles don't necessarily have to be touching, just like they are. And I'll show you another visual of this too. Here are your natural numbers. Okay, and we abbreviate them with N. And numbers would be like 1, 2, 3, 4, 5, and so on. Okay, because I want to show you this other thing. Yeah, a little too much to Mrs. Talley all of a sudden. Here's what I got. We've got our container, and I'm realizing, oh, it's backwards for you. I'm so sorry, but I'll have it in class so we can look at it this way too. So the numbers that would go in the natural container, and if you had me for algebra, you might have seen this demonstration already, but it's not going to hurt you to see it again. Numbers like 1, and of course my numbers are going to be backwards, so I'll just say them. 2, 3, 3,000. Granted, most toddlers can count that high, but it's a natural number. And square root of 36. It's backwards, I'm sorry. Square root of 36 is 6, which is a natural number. 8 over 2. 8 over 2 is 4, and 4 is a natural number, so it goes into this natural container. Okay, so those are just a small amount of natural numbers. All right, imagine them in this container. I'm going to put this container right here. Okay, let's move on. What's after natural numbers? Whole numbers. Whole numbers are natural numbers plus, and this is my joke, this is the Mrs. Talley right there, the whole, because whole has W-H-O-L. Oh yeah, that's just so crazy, because the only other number that's added to this, beyond this, is the 0. Look, notice my list here. Okay, so whole numbers are all the natural numbers plus 0. And I think of a hole in the ground, it makes the shape like, this is why I have this little funny dot there. When you make a hole in the ground, it's like that, it's like a 0. Yeah. All right, so on your diagram here, holes. Okay, we abbreviate that with a W, and the only number that I'm going to put in this whole circle, just the yellow part, is a 0. Because I already have 1, 2, 3, 4, 5, and so on in this circle, and this green circle is already in the yellow circle. So we're calling her good. We've got the numbers 1, 2, 3, 4, 5 in there already. So what does that look like with our picture? I believe here's my number 0, which is good because it looks right, even backwards. All right, and it goes in my container that says holes. It's just the W for whole numbers. All right, I put this in here, but 0 is not the only whole number. The numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to put the natural numbers inside my whole number container. All right. Okay, let's move on. What's after whole numbers? Well, integers. Okay, integers. They're the whole numbers and their opposites. Okay, now here's the thing. Recording, when I was looking in the book, and this is actually news to me, we should be abbreviating integers with a Z. And it's Z for this word Zahlen, which is German for the word count. Now, the numbers that go in for integers would be -4, -3, -2, -1. 0 is already up here for your whole numbers. And so they're opposites. The opposite of 3 is -3. So that's what I mean by their opposites. So whole numbers, 0 on up, and their opposites, all the way down. Okay, and we abbreviate integers with a Z, which is probably the first time you've seen it as well. And from here on out, you should see it as a Z. Let's go ahead and put this on our chart. So here's my Z for integers. And I'm going to put a couple numbers like -1000. I could put 1000 in there, but 1000 would actually go in this circle, which is actually in the orange circle. All these circles are inside each other. So then I could also put -22, -4, -3, -2, that's supposed to be a comma, -1. 0 is already in the circle. Okay, so on and so forth. I could even put -100 over 2. Well, -100 over 2 is -50. -50 would be considered an integer. All right, so let's move on to my diagram. Here's the integers. Oh, and integers should be abbreviated with a Z. Okay, so here's my bucket. So I've got numbers like -1. Oh, I know it's backwards. -1. You can't tell that. -2. -3. -4,000. -5,000 over 2. All right, those would be considered integers. But isn't 0 an integer? Isn't 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, aren't they integers? So the whole numbers and the natural numbers, there's my other container in there, are all considered to be integers as well. So they get to go in the bucket. All right, moving on. After integers, we have rational numbers, okay? So when I say rational, I mean fractional. That's, once again, what I call a Mrs. Talleyism, I guess. Now, the abbreviation we're going to use is Q. And you're like, whoa, Q has nothing to do with rationals. But yes, it does. Because Q is for quotient, because rational, fractional. And when you are a fraction, you're actually dividing, right? So you're dividing the two numbers. And what's the solution to anything you divide? It's called a quotient. Remember, addition is sum, subtraction is difference, multiplication is a product, division is a quotient. And so when you're dividing, you end up with a quotient, and therefore you have Q for the abbreviation, because once again, that's kind of a new one for me. Now let's look at the different kinds of numbers we've got here. -1/2. Yeah, that's a fraction. -0.75. You're thinking to yourself, Mrs. Talley, that's not a fraction. But can't you write -0.75 as a fraction? Yep, you can. -3/4. 0 is already included up here as a whole number. 1. Here's the famous one, 2/3. What's the decimal equivalent of 2/3? 0.6 repeating. So repeating decimals also are considered rational numbers. So there's a 0.3 repeating. And this is 8/2. Well, 8/2 is 4, and 4 is a whole number. It kind of goes under the same classification there. Not kind of, it does go under that classification. So rational numbers, in my mind, rational, fractional, rational, fractional, rational, fractional. Okay, let's put that on our little chart here that you should have going in your notes. Rational numbers, Q, okay? -1/2, -3/4, -0.75. I could put numbers like 0 and 1, but they're already up here, so I don't want to relist them again. They're already in the red circle. 1/3, 0.6 repeating. Anything that has a repeating decimal would be 0.2371 repeating. If the whole thing repeats over and over, it would be considered a rational number. Okay, and one more thing to kind of hit this home. Q here is my container for rational numbers. Once again, it's backwards, I'm sorry. Some numbers that would go in there. 2/3, 7/8, -4 1/3, -5.2, 1/3, and I didn't put, it's a repeating decimal, but 1/3 is 0.33333 repeating, actually 0.3 repeating. All right, they all go into the rational box. But aren't numbers like -4 rational? Because can't I write that as a fraction? Rational fractional. So -4 would be like -12 divided by 3 is -4. So that's a rational number too. In fact, every number that we've listed in the integer box is considered rational. So guess where all of these go? They go in the rational box. Moving ahead. Okay, irrational numbers, which we give I as our abbreviation. Whoa, irrational numbers. If somebody has irrational behavior, they might say they're crazy, insane. That might be a little too harsh, but it's kind of like a way to say that they're not doing the normal behavior. And that's what happens with irrational numbers. They're not necessarily behaving what we consider normally. Pi, what do we all know? I mean, it's the most famous irrational number of all. Yeah. Why is that? Because pi goes on forever and ever, and it never repeats. And little do we know, most of you guys, you type in square root 17 into your calculator, and you're like, woo, square root 17 is this decimal. This decimal, your calculator cannot show you, and even this decimal, it keeps going forever and ever, just like pi, and never repeats, just like pi. Okay, negative square root 6, once again, a decimal that never repeats, and it never completes. And the other way to write some of these things is to write like -2.377263 ... That dot means that this number continues and we have no repeat bars. So we know that this number goes on forever. It's the number that never ends. Here's another one, 0.4268 ... That number keeps going forever and ever and never repeats. We call it irrational. All right, so where does that go? Well, this actually gets to go to this, this location over here. This blue, which maybe I need a different color here so you can see it. They're called irrational numbers. Whoops. And we abbreviate with an I. Put that like that. And they would be numbers like square root 3, square root 10, 1.2364, ... You need that there. The negative 1.3617, and if you do not do anything besides this on a test or a quiz, it will be wrong. You need to put the dots to show that. Okay? Now, and to kind of summarize this out, let's take a peek. These numbers that would be irrational, negative 3.6214, ... 1.37268, ... negative square root 18, square root 15, pi, the most famous one of all. And once again, I'm so sorry, it's just backwards and I don't know how to even, irrational numbers, okay? They are going to go, all these numbers go into this box. But wait a minute, that's kind of interesting. This irrational box, and I have a rational box. There's no overlap. None of these numbers go into this category, and none of these numbers go into this category. They're like two separate entities, but they're all numbers we know. All the numbers that we are aware of at this time in our lives. We call them real numbers. So I'm going to put this in the real number box. The irrationals are considered reals, and the rationals are considered reals. And once again, backwards. Kind of killing the lesson a little bit, isn't it? All right, let's go back here. And what I did is I put reals. Oops. Hold on, we can fix this. What I did is I put reals over here along the left side. These are all considered to be types of real numbers. The scary thing is, later this year, we will find out that there are such things as non-real numbers. Okay, so what I would do on your chart, so if you've got these circles going on, I would put a big box around it and call the big box the real numbers. Okay, let's do a couple practice here with that. This is from the book. I'm going to make this optional because it's a lot of wordage, but I think we just need to hit that one more time. Rational number can be expressed as a ratio. The decimal form of a rational number is either a terminating or a repeating decimal. So if it's terminating, it's like 1.9. Repeating would be like 2.575757 dot dot dot, but you're going to have to be smart enough to say that's 2.57 with the bar over the top. Okay, what do I mean with that? 2.57, oh, that's not going to be seen. 2.57 would be the same thing as this. Okay, and then of course irrational, a real number that is not rational is irrational. The decimal form of an irrational number neither terminates nor repeats. And once again, pi is your perfect prime example, but what if I said, give me more than one example of irrational numbers? You need to come up with something else. So square root 5, go to your radicals. Be careful, don't put down square root 36. Square root 36 is 6. Okay, name the sets of numbers to which square root 6 belongs. Okay, well, square root 6 is an irrational number, so I'm going to put down an I. And then I'm also going to put down what I call the double-leg dart. I never talked about this. That's why I say it's a real number. So I have square root 6 belongs to the real numbers. Name the sets of numbers to which 5 belongs. Well, 5 is a natural number because you learn it naturally when you're learning to count. It's a whole number. It's an integer. Oh, wait a minute. I'm not supposed to use I for integer. Q. No, Z. Sorry. Z is going to take me a little bit to do. We got integers, and then it's also a rational number. And so something's rational. I think we're putting down R. And then it's also a real number. Oh, wait, no, R, not R. I would stop and start all over, but I just have gone too far. It's a Q. Q for rational. Can I just put that down there? Integer, because it was probably a little misleading. And this is the real numbers, the Q's, because they're quotients. Oh, I wrote it down wrong, you guys. You're going to be like, this is Talley. It's not. It's rational is the word I'm looking for. Sorry. Oh, I'm so sorry. Okay, negative 2/3. This number right here. It's already a fraction. Rational. Fractional, rational. So once again, I'm going to do this right. I'm going to get right on the first time. Q, or rational. And then, of course, it's also a real number. Name the sets of numbers to which negative 43 belongs. It's an integer. I put down Z for integer. Okay, it's also a rational number because I can write it as a fraction. Negative 43 over 1, I suppose. That's kind of a cheesy answer to that. So I'm going to put down rational, and it's also a real number. And negative 23.3, I could write that as negative 23 3/10. There's the fraction. Fractional, rational. So it's a rational number. So I put down Q, and then it's also a real number. All right, anything else? Nope, that's it for this portion of the lesson.